Want to nail engineering manager interviews at Mang and other top-tier companies? You can with USA's #1 tech interview prep platform. We have 300 plus SMEs and instructors from top-tier tech companies to help you land your dream job. We've helped thousands of engineers make their way into Mang. You could be next. To learn more, register for our free webinar.
Okay, so those are your questions. How do you want to start?
Maybe we could start like at a high level about versus like what's your thoughts regarding conformal prediction and how that compares with other uncertainty estimates that you're more familiar with?
Yeah, I really like this paper or article, a general introduction to conformal prediction. It
Okay.
has all the details, so I think it's really good, and also it's very well written, and it says the theory and give examples. So so you understand the conformal prediction basic idea, right?
I think so, mostly.
Yeah. So my thought about this is that I like this algorithm a lot. The only problem I can see here is, I mean, it like no one really mentioned this, but from my opinion is that you need to reserve a data set for the calibration
Yeah.
data set. Yeah.
Yeah.
And because when you reserve a data set for calibration and you are looking for quantile, right? In the calibration, you are looking for the quantile.
Right.
So which means that your calibration data has to be relatively large. For the original CPE process, maybe you don't really need that because they just compute the error and just
Yeah.
use the same error for every estimating point. But for the future development, like adaptive,
Right.
I believe this is going to pose some problem because if you have the data set, usually people will prefer that you train those data set in your training in training.
Yeah.
A lot of, especially like machine learning, deep learning algo, they're also very demanding on the data points. So if you have the extra, I don't know if you have to think about this. Do you have the extra point for the adaptive prediction? So this is something I can see that first point is that the calibration data set can be problematic in reality.
So maybe if you can first explain your thoughts about what is adaptive prediction. Is that the prediction interval is like the width may actually be different depending on the data points, or is there another definition?
Actually, some of them don't do that. It really depends on which one we are talking about. If just the regular adaptive, they probably don't do that. So they are saying, but there's one kind of adaptive, I think, here, right? The adaptive here, it doesn't really change the width of the interval. And so you can see that first they use the quantile regression. So to get the upper bound and lower bound and adjust that based on the quantile regression results. So if you use this, even that the width is going to be the same, right? Probably not here. Where is the formula? Anyway, after they do this, maybe not this paper. So you can see that if you do a really simple adaptive, the first step they do, I believe they are going to get some. They are going to be adaptive based on the estimate points because they use the quantile regression, but it's still after you have the evaluation, the Q hat and the Q hat is shared, right? So the width is kind of fixed for the CP. So I don't think even for adaptive, I don't think it's going to be that useful. I mean, I should not say it's not useful. I will say that if you want to get a really good result, looks like you want to reserve a quite significant amount of data for calibration data set.
Okay.
I don't have experience doing this actually, so I don't know if you have tried this by yourself. Have you tried this with real data set or simulated
Yeah.
data set?
I can show you now. Well, whenever you're ready.
Yeah, yeah.
Okay. So this is a notebook. So this is I'm using a energy data set, which looks like this, very strong seasonality. And then this is if I plot it as like a line. And then this is if it's a scatter plot, is every hour for the year of 2015. So here, what I'm doing is just taking 3 models, all of them near profit, with various different configurations. So this is the one most likely like profit. This is the one with auto regression, but just auto regression, and then this is the one with the ARNet with hidden layers. So this is the simplest. This is the most complex model, and then so I'm just training it normally. And then first thing is I am splitting it into 4. So I have train, validation set, calibration, and test set. I just had validation set, although I don't really need. Actually, I might need. I'm not. I don't really need it since I'm not looking at like different hyperparameters. But I just have it just in case. So, um, so first is I train with the train set and then validate with the validation set.
So when you split, this is time series data. So when you
Yeah.
take the data set, how do you split into chain, or you just split that?
Yeah. So you can see the ranges of the time. Training,
Okay,
validation, calibration.
I see. Yeah.
So training is first, then validation is second, calibration is third, and then tested is last.
I think this is a good design. Yeah.
Okay.
And looks like you have a abundant of data also.
Yeah, this is just an example. And then this is the plotting just for the train. And then so you see cuts off at early August. So now I have these 3 data, and then I'm training a train set, validation set, and then so here are just testing it. First, I'm plotting it on in sample. So I'm plotting, so I'm predicting the training set, and then so here I kind of expect they all fit pretty good, but even for this one, you can see that the more complex one fits the best.
Yeah.
And then same for validation set. So now for test set, this is the one that's out of sample. And then, so this one has not been touched. So then this is the results. So you can see that the simplest model doesn't perform that good. But when you go to the more complex one, it still fits pretty well. So then now this kind of gets to the conformal prediction. So here, I'm currently working on 2 types of conformal prediction for regression. And right now, this is just one step forecasting, just to simplify it. So the first way this is not conformal as Quantile regression. That'll be next. The first way is just to have a regression, and I get the non-conformity score or conformity score of the absolute, like the distance or the difference between y and y hat. So I select the alpha right here, and then I get all the scores for each one. So this is the non-conformity score, and it's just the difference between y and y hat for the calibration set. So when I'm training it, I'm only training using the training set and the validation set. And then so how I'm getting the results is I'm using that train model to predict the calibration set. And that's how I get the actual value as well as the predicted value. And the difference between those two are the scores. Then from the like the algorithm, I take the alpha. So non-conformity score, that is the higher the value, the more non-conformist it is, or the higher like the residual or error. So the goal for alpha is I want to get the coverage of, if it's 0.1, then I want to get the coverage interval, like the coverage of 1 minus the alpha, which is here is 90.9 or 90%.
Yeah.
So what this is doing is I want to see what is the score and then get the 90th percentile score of it, and then I will then apply that as the interval width. And then so here is kind of getting, so I'm getting the index, and finding the index, and then times alpha, which is 74.67, and I'm getting it from the right-hand side. So the scores is sorted by in ascending order, and I'm taking these from the right-hand side. Alternatively, I can also do 1 minus alpha here.
Yeah.
So I get, these are the actual Q values, and then you can see it plotted here. So this is the 90th percentile score for Q1, Q2, Q3, and then you can see, it's interesting.
How come so what's the blue line, the score?
Okay, so this changed a little bit because so here maybe I need to train again. So here the blue line that you saw is all the non-conformity score, and that is sorted ascending. And then the orange line that you saw was the Q value, which is the value at the 90th percentile.
Yeah.
Yeah. And then, yeah, so I'm now just retraining the model again. It'll probably take 1 or 2 minutes. And then I can show it to you again. And then, so I think this is where I am here. So we can show that out of my numbers, right? Because I'm getting the Q index, Q value for each of it. And then I'm plotting it. And then next step is once I have the Q value, I'm applying it to both sides. So y hat minus Q is y Q1. Y hat plus Q is plus Q1. So I'm getting the Q value, and then I'm adding it of the predicted value, and then that's how I'm getting the prediction interval around the predicted value. And then the goal of this is that since calibration set is out of data from training set, for future, when you're making future predictions, the goal of the prediction interval is that there is a y minus alpha chance that that future y value is within that prediction interval, or 90% chance.
Yeah.
So that's the go, but then it kind of comes in. That's where a lot of complication of, is it really that reliable? At the same time, you want it to be reliable or valid, but you also want the prediction interval to also be very, very narrow as well.
Yeah.
So it's not going to cover too wide. Otherwise, that would be less meaningful. So now I have that again. So you have the different Q values, the score here, and then so this is the results. This is still in sample. This is what the calibration said. So I think overall plots pretty well. But then this is the interesting part, is where I'm using auto sample with the prediction interval.
Hold on, what's the difference between the earliest one and this set? Oh, the L1? What's the difference between go up? I know you built 3 models, right? And what's the difference between this set, this 3, and the following 3?
So this one, this is in sample. I'm plotting it. So this is still on calibration set.
I see.
So this should pretty much match for all of them.
Yeah.
But then the next one here, this is out of sample. I'm predicting on the test set. So here, you can see that this is the weakest model. Quite a bit is still outside of it. But then these two models, you can see that because they're stronger performing models, they have overall less conformity scores. So they have narrower width.
Yeah.
But even though they have narrow width, it still kind of encompasses these points pretty well.
Yeah.
And then the final check is actually using something called validity, which is basically validity is basically just calculating the percentages of this out of sample test set. The actual data points are actually in the prediction interval. And M1 is the simplest model, so that's the highest one. M3 is the most sophisticated one, has the narrowest interval. Yeah, they both have similar. M3 actually even has a better validity.
Yeah.
So that's saying even though it has a narrow width right here, it is still more reliable than this one here.
That's nice.
Thanks. So that is for the first version of the conformal. That's for the conformal prediction with a simple non-conformity score. So now the next step is actually using conformalized quantile regression, which is this. So for now, I'm just using the low quantile as 0.5, high one as 0.95, and then so you can see that here, this is the quantile regression, and for the 3 models, and you can see that this is the weakest model. It's not very reliable. Even this is supposed to be 95th percentile. That's saying that 95% of the data is supposed to fall under here, but you can see that's not the case. But then for the more recent one, number 2, number 3, you can see that it's fitting better and better.
Yeah.
So now the next step is kind of how to apply conformal quantile regression here. And so this is out of sample. I'm kind of repeating what I did before. Now this is the nonconformity score. And then this is the formula from the conformalized quantile regression. So unlike the last one I did, I used the y hat. Here I used the y hat of the 5%, and then the y hat of the 95%, which is the quantiles right here. And then use that with the actual value, and then use that to calculate the nonconformity score. And then I did that here, and this is what the values look like. So I think this is the okay. All right. So then I think the goal here is to actually apply the quantile, this conformal prediction on these quantile right here. So here you see there's like 4, and that's actually kind of like where it's it gets a bit confusing. Yeah, so here maybe I can try another example. Hopefully this looks better. Yeah, so this is I just recently coded it right for our meeting here. It's still very fresh. See how that looks. And so something is happening. Okay. Why have I this? Yeah, so that's more or less that's kind of like the demo. Oh yeah, maybe I didn't. Did I run this? This should have it. Okay. This should work. Okay, so you see that if I try to make here you can see that there's this quantile that's 2 quantiles that's kind of hugging this quantile right here, this original quantile regression. And here's the conformalized quantile regression right here. And I think that here, then you'll use the upper bound of this to then use that to make the adjustment of the quantile here. So maybe if I change, do you have any questions so far?
No, I follow your logic, and looks like the performance is really good as well.
Yeah.
So, yeah, I have a quick comment is about, you also mentioned that the exchangeability. When you look at your data, it's actually not exchangeable, right? Because you can see that there's a clear trend. T1, T1, T2,
Yeah.
T3 is not like the probability is not going to equal to T3, T2, T1. I mean, because like you said, the seasonality is so strong here, so the exchangeability is not going to hold. But you kind of resolve the problem by choosing your calibration data set, verification data set, and the test data set, etc. because you kind of take period of time, and period of time. So because they need to use the exchangeability is because when they choose the calibration data set, which is like you can randomly choose a data set. But now when you do the time series here, you are taking kind of repeated pattern. So that's why you don't have any problem here. Even you can see that the exchangeability property is not here, but you are still doing okay. And I think this is fine. As long as you are doing that, you kind of do your calibration data set on a certain period of time, and you believe that the pattern is kind of hold. And all the models assume that, right? So you kind of overcome the difficulty by choosing your data set. So this is very nice actually. You can write a paper on this actually, because when I read the temporal CP paper, they didn't even mention this. They emphasize that you have to be exchangeability, and also they give an example is like a readmission. So if it's readmission, maybe they can use they can assume that the data set is exchangeable. But when you do something like this, I think it's okay, even it's not exchangeable. So that's why I say maybe, yeah, it's worth to publish your findings.
So you're saying that, well, I think this gets into like kind of the data set, which is the energy data set. So that's pretty strong seasonality. So that's why I think that this is able to forecast somewhat accurately even out of sample, since it's very repetitive. But for more like real world time series, for example, market prices, stock prices, or like other like sensor information, maybe even weather. That is where exchangeability assumption like applies even less. And I think that those are all the questions I have, which is what additions that I need to like make in order to be able to for this to also like be utilized reasonably well for those more complex time series.
Yeah, this is what I suggest. Maybe try different data set, which the seasonality is not as strong. You can maybe the exchangeability problem will come up. I'm not sure. I'm just assuming.
Right. Okay.
But overall, I think you are doing great. I think you know the algo from inside out. That's why you can code all this, right? And the implementation is also great. I would, like I say, I would suggest you try more challenging data set.
Yeah.
This is the only thing I can think of.
I think another next step is also like more like multivariate. I think as we discussed,
Yep.
like covariate. Currently, this is just univariate, and then multiple time steps. Yeah, so there's a lot of different ways, and then other data sets as well. So there's a lot of ways to further, further test this.
Yeah, exactly. The paper you sent to me about the temporal quantile adjustments is actually has a 2 dimension, right? One is the longitudinal part that you have
Right.
that, and another is the cross section. We don't you in your example you don't have a cross section here.
So cross section is that. So that means there's longitudinal. That's just the temporal part, and then cross section that is the lag covariates, right? The other time series.
Longitudinal is more like a time series, and the cross section is more like you have multiple patients, or it's more like a multivariate.
Multivariate.
Yeah, I mean you just mentioned that. I think just use different term.
Okay. So is multivariate time series just one time series, or could it also be multiple univariate time series?
There are many ways of doing that. I think the most recently people use covariate, so you can do one-hot encoding.
Okay.
Yeah, there are many ways of doing that, but I tend to build the same model because if you want to build like, it also depends on the size of the problem. Usually, when I deal with the products, we have more than 200 products, more than 200 products that need to forecast. Then, if we build 200 models, that's certainly too many. It's not just the implementation will be difficult, so you have to be creative. So usually we use some like a one-hot encoding, or maybe sometimes we cluster some of them into like 2 or 3 models instead of building 200 models.
Instead of using one or two more instead of 200.
Yeah, if I cluster some of them, right? Maybe I cluster like 200 products to 5 categories, and I build like 5 models instead of 200 models. There's also a way to avoid too many models. We don't want to build too many models because the maintenance will be expensive.
Right.
And also you need to think about that if there's a new product coming in,
Yeah.
how you are going to use. Yeah, if you build 200 models, it's difficult. If you have a model category, you know the characteristics for those categories. Then when the new product comes in, you know which category it should be belong to. So for all those reasons, we don't want too many models.
Okay. Yeah.
Okay. And yeah, I think you did really good. And when you reach this point, I think you understand all the difference. I mean, in your email, you talk about exchangeability versus RID. I think you probably know that already, right?
Yeah, I think yeah, that was when I sent you that email. Like, because I did a lot of work in
Yeah, I can see that. I think you probably understand the material inside out right now, instead of when you just send me the email. Yeah, like came in, it's kind of clustered. I think after you do this exercise, I mean, it's really good work, and you probably know the algo very well already.
Okay. Yeah.
Do you have any other question or anything that I can help?
Uh, Given that what I showed you, maybe I guess based on your experience with time series, whether you have any like pointers of what things that I might need to be aware of, especially if I want to implement this conformal prediction intervals for various type of time series.
Yeah, I think like we discussed already, I will try more difficult data sets. Looks like this data set has really strong similarity. So the exchangeability problem just get resolved because of the way you break your data set into training, calibration, validation, and test. and you probably won't be that lucky if the trending is not that. You can see that, especially if the volume is kind of up or down happen to be in your validation, in your calibration,
Mhm.
then your interval will be too narrow. If you apply to a test that's got the the quality, the volume is getting higher again. You know what I mean? Like in your example,
Yeah.
if you happen to be build a model on the first two cycle, and then you use the second two as the calibration, and then the
Okay.
after 3 what, and then you use the last 3 cycles for the validation, then probably it's not going to work that well because the volume, the quantity in the calibration is smaller. Yeah.
So you're saying calibration data set has to be representative of what might be out of sample.
Yeah. This when you say represented is actually another word for the exchangeability, right? Not exactly, but which means that
Yeah.
you can just because the exchangeability just means that you randomly pick up something, then it's going to be representative to the probability that you are going to forecast. Your model is training upon. So it's kind of
Right.
match the idea. It not exactly, but it's a similar idea.
Okay.
The only difficulty I can see is that, like I said earlier, you probably will need a larger calibration data set to make sure that the algorithm works. And if you have the kind of luxury, usually people would like to put it into training instead of the calibration.
Mhm.
But in practice, it's probably not a really bad idea. I just saying in practice, it's probably not a really bad idea that you also use your training data set into to design your quantile. I know this is probably in theory is completely wrong, right? Because you are kind of doing the prediction already. But maybe
Mhm.
it's a good starting point. Maybe it's also another research possibility is that I also use my training data set for my confidence interval. They don't call it uncertainty. They call it what? Uncertainty qualification or something like that. UQ or something. Yeah. So maybe maybe we can do that and kind of do an adjustment on the calibration data set. I don't know. This I believe maybe a lot of variety is possible, but at least I think this is a pretty new topic, and I like the quantile regression to start with, and the error is actually built upon the model. I can see the developer on this. Uh, yeah, I think it's more understandable in being model.
Yeah. So I think quantile regression by itself is that this is derived from the training data set, learning and the model produces. Like it produces mean, but also produces those values in those quantile. Uses a loss function called pinball loss. And then, so this is what you have here. And then the conformal prediction is kind of like this one. So the blue part here is that's the initial quantile regression. Then the red part is that conformal prediction, and you can use the red part as like a way to kind of adjust
Yep,
quantile regression.
yep. To reduce the width.
Reduce or even expand the width depending
Yeah.
on how well, and then that's like if the original quantile regression undercovers or overcovers.
Mm.
And I think usually undercovers. maybe it's like too confident. But then we use the conformal prediction, the intervals, as a way to as a sanity check.
Yep.
Yeah. I think, for example, like this point right here, this conformal quantile regression does not cover it, but then when you have the conformal prediction, it actually also covers this point right here.
Yeah. It's difficult to see in the middle, like between the drop, there is something between the middle, right? I cannot really see why did you know where I'm talking about? I'm talking about between the cycles, they have a point over there. I mean, from your the chart, yeah, this chart.
Yeah.
So there's a point there, yeah. Where you point, yeah, those.
Right.
There's no confidence interval at all on those points. I don't know what's going on there.
There is. It's just really tiny.
Mm.
It's like very small. I think that
But,
this is
but why is that?
Yeah, I think that's a good point. That's something I need to look at. Yeah, since I presume that they're supposed to have the same Q. But this is Quantile, so Quantile it kind of does its own thing because it learns it. Let me check. Let me see this one here. So okay, so this one looks more clear. I think this is I think these are still the same interval, like right here, but because it's dropping so much, it seems like this is like a narrow thin, but if you like put a straight line, it still has the same width. That's my guess.
Yeah.
That
Yeah, so it's just visibility. Yeah. So what are you working on? Why do you join the Interview Kickstart?
I did a few interviews. So Google, Meta, I couldn't pass the technical screening because I don't think I prepared enough for the algorithm part. Mostly because I was too preoccupied working on these research stuff. Market's getting better. And then number two is I'm hoping to use this also to kind of further develop my skill sets as well as something else that I can put on my resume. And then since at work, I do learn some things, but it's not as like intense and hands-on as working on this. And that this is something that I can also take away with me as well.
I see. Yeah, I think you did a really good job, and yeah, I'm happy to connect with you and let me know if there's.
It also kind of goes back to like I kind of wish the interview process is more kind of like this. It's like I can like it's more like a demo kind of showcase.
Yeah.
Of interesting things that you can do rather than just lead coding. And that's actually a reason why I changed from being a software engineer to data scientist is I can do engineering, but I definitely like data, discovery, analysis, and more. But then if I have to go and do lead code again, to do coding, then I can really demonstrate these capabilities. And then, yeah.
This is really great. Like these days, especially when we are hiring applied data scientists, we like someone who has some engineering background. So it's definitely really good for you.
Yeah. But does the applied data scientist need like a master's or PhD?
No.
No? Okay.
Usually we don't hire PhD. Maybe sometimes we look for master, but it's not a requirement.
Okay.
It's more like hands-on experience and presentation skill, like you are doing here. And yeah.
Yeah, gotcha.
Okay.
Cool.
Yeah, it's really nice that you show me the notebook. I think it's really interesting and exciting. Let me know if you make some progress on the other data set. Will be really interested. Very interesting to see. And I believe you are doing great.
Thank you.
Okay.
Yeah. So once I clean this up a bit, I can also share you this notebook as well.
Yeah. Feel free to reach out me to LinkedIn, and like I say, I'm really interested in the work that you are doing, and so
Awesome.
yeah.
And I hope, yeah, we hope we can keep further in touch. I think
Okay.
I have made some progress almost on a daily basis, and I can let you know whenever I have some milestones, and I can also share with you.
Yeah. Okay. I really think the uncertainty quantification is going to be really important in the future. Look at the mean doesn't make sense at all. People want to know the risk, right? When you make a
Yeah.
decision, how far you are away, you want to have some idea about this.
Yeah. At the same time, like using like distributions, is it like Bayesian methods, I guess. Without assuming that is a normal distribution. I mean that could be very like computationally intensive.
Yeah, exactly. And I don't think the result is really promising as well. At least I don't see many people are using Bayesian. Even in theory, a lot of literatures there, but in practice, I don't see a lot of applications there. Maybe there's another way, because just the approach itself is much easier to understand, right?
Yeah, I think that's the reason why this area, conformal prediction, what I'm showing here is blowing up.
And the theory is also beautiful. I don't know if you see the proof, but the theory about how they adjust that, and then some theorem that is going to cover, that's also very beautiful.
From which paper?
In general, I mean,
Okay.
when they do they use the quantile regression, and then do the adjustment, and then they can prove that the interval is going to cover at least 1 minus alpha percent probability.
Oh,
Those
you mean the? Let me see which paper. You mean this paper?
Yeah, this one is more advanced. There's another one just improved something.
This one.
Yep.
Okay. Okay. Cool. Yeah. Take a look at this paper deeper.
This is okay. I don't think. Yeah, I am just saying that the theory is also beautiful, but I don't think that this is that important. As long as you know the property, I think it should be good.
Okay. Okay. So this one's using the unsupervised process and then cluster different.
Yep, they use cluster, but they have a pretty good introduction on the whole process.
Oh, you mean this? Okay.
Yeah.
Yeah. Got it.
Yeah, thank you for your time, and really nice to talk to you.
Yeah. Likewise.
Okay, let's keep in touch and maybe collaborate in the future.
Yeah. Sounds good.
Okay, yeah, talk to you later.
All right.
Thank you. Bye.
All right. Bye bye.